The nucleus, what we know, and what it means. An augmented Newtonian dynamics presentation. Before the nucleus, matter as a continuous medium. Atoms were not known to exist before the early 20th century, although philosophers had speculated about them for more than 2,000 years. For most of scientific history, matter was believed to be smooth, continuous, and uniform, an unbroken substance that could be divided without limit. Energy, too, was imagined as something that flowed continuously, without any hint that the physical world might possess an underlying granular structure. The idea that matter consisted of tiny indivisible units was treated as a philosophical curiosity, not as scientific reality. A turning point arrived in the early 19th century, when John Dalton introduced a quantitative atomic theory. He showed that elements combined in fixed, whole-number proportions, and argued that unseen atoms explained this striking regularity. Dalton gave atoms scientific legitimacy, but not yet empirical certainty. Many physicists still doubted that atoms existed in any physical sense. Einstein, Perrin, and the establishment of atoms. The debate ended a century later. In 1905, Albert Einstein explained the random Brownian motion of tiny particles suspended in water. Their erratic dance, he showed, was caused by countless collisions with invisible atoms. Jean Perrin's meticulous experiments soon confirmed Einstein's predictions. Within a few years, the existence of atoms was no longer speculation. It was established physical fact. Yet their internal structure remained unknown. The early model of the atom. Early 20th century models imagined the atom as a soft, diffuse sphere, a smooth cloud of positive charge with electrons embedded inside it, like raisins in a pudding. Nothing in these models suggested that the atom might contain sharply defined or highly concentrated components. This picture was overturned suddenly and dramatically. Rutherford and the discovery of the nucleus. In 1911, Ernest Rutherford fired alpha particles at an ultra-thin sheet of gold foil. Nearly all of them passed straight through as though the atom were empty space. But a few rebounded sharply, as if they had struck something dense and extremely small. Rutherford later remarked that it was as surprising as firing a heavy shell at tissue paper and having it bounce back. In that moment, the nucleus was revealed, a tiny, extraordinarily dense core containing over 99.9% of the atom's mass, while occupying less than a trillionth of its volume. Matter was not continuous after all. It had structure, deep, concentrated structure, hidden at its center. 2 decades of mystery. For more than 20 years after Rutherford's discovery, the nucleus remained enigmatic. No one knew what it was made of. No one knew why it weighed so much. Some believed electrons must be trapped inside to balance charge, but this explanation created contradictions with beta decay. The nucleus was known to exist, but its internal architecture was still hidden. That changed in the 1930s. Chadwick, Strassmann, Hahn, and Meitner, and the first true glimpse inside the nucleus. In 1932, James Chadwick discovered the neutron, an electrically neutral particle almost identical in mass to the proton. The nucleus finally had a clear composition, protons and neutrons. A few years later, in 1938, Otto Hahn and Fritz Strassmann found that bombarding uranium with neutrons produced elements far lighter than uranium. Lise Meitner, analyzing their results while in exile, realized what had happened. The nucleus had split. Nuclear fission had occurred. A vast amount of energy had been released, confirming that the nucleus contained immense internal binding energy. For the first time, humanity understood that the nucleus was not just the heart of the atom. It was the heart of matter itself. What lives inside the nucleus? The nucleus contains 2 heavy particles, protons and neutrons, collectively called nucleons. Their masses are almost identical, around 940 megaelectron-volts each. By comparison, the electron is tiny, only 0.511 megaelectron-volts. Yet even these massive nucleons are not fundamental. But here lies one of the most striking facts in physics. An up quark weighs only tilde 1.8 megaelectron-volts. A down quark weighs tilde 4.3 megaelectron-volts, so 3 quarks contribute only 8 to 10 megaelectron-volts, yet the proton or neutron weighs almost 940 megaelectron-volts. The quarks themselves provide almost none of the mass. So where does the mass come from? E equals mc squared, the most beautiful equation. There is an equation often described as the most beautiful in physics, E equals mc squared. Its beauty comes from what it reveals. Mass is not an ingredient inside matter. Mass is simply internal energy, energy of motion, energy of binding, energy of structure, confined and stabilized. Inside the nucleus, this becomes unmistakably clear. Almost all of the proton's mass comes from internal energy, the dynamic processes, tensions, and confinement that hold the nucleon together. Quark masses contribute only a few MeV, internal energy contributes almost 1,000. This is why the nucleus contains nearly all the atom's mass. It is why nuclear reactions release extraordinary energy. It is why the sun shines and why elements form. E equals mc squared is not abstract here. It is the practical explanation for the existence and behavior of matter. The nucleus is its clearest demonstration, mass as concentrated energy held in a stable form. Gluons mediate the strong force. Gluons are massless gauge bosons similar to the photon. Gluon interactions operate only at sub-femtometer distances. Beyond about 1 femtometer their influence drops to zero, confining them strictly inside nucleons. Unlike ordinary forces that weaken with distance, the gluon force increases as quarks are pulled apart, like a stretched rubber band storing more tension than a relaxed one. But because this rising force acts only within distances smaller than a femtometer, it cannot exert influence beyond the nucleon itself. Thus nucleon forces do not arise from gluon exchange. At nuclear scales, interaction occurs only through short-range contact forces between nucleons. The augmented Newtonian dynamics view, internal stabilization cycles. In augmented Newtonian dynamics, this internal energy is not treated as an abstraction. Every particle maintains a continuous internal stabilization cycle to preserve itself. For the electron, this cycle is rapid and high frequency. For the nucleons, it is slower but immensely energetic. Mass is the total energy contained in this cycle. The nucleus is therefore not bound by a probabilistic cloud or quantum potential. It is held together by the compatibility of these internal cycles. Bring two protons together inside a femtometer, and their cycles clash violently, far more strongly than their electrical repulsion. This is why the diproton does not exist. Bring a proton and a neutron together, and their cycles synchronize. This is the origin of nuclear binding. Nuclear structure becomes a question of cycle alignment or cycle conflict, a classical, intelligible mechanism for stability. Internal cycles as the physical meaning of spin. Quantum mechanics assigns every nucleon a property called spin, a quantity that behaves like angular momentum even though no particle is actually rotating. In theory, this behavior arises naturally. The internal stabilization cycle gives each nucleon a persistent directional character in its energy flow. When nucleons come together, aligned cycles stabilize, opposed cycles destabilize. What quantum mechanics describes as spin coupling is, in theory, simply the mechanical synchronization or desynchronization of internal cycles. This removes the abstraction and replaces it with physical mechanism. Building the elements. Geometry and cycle compatibility. As more nucleons gather in the nucleus, these cycle interactions determine which combinations are stable. A proton introduces cycle conflict, a neutron reduces it. Light nuclei therefore tend to have nearly equal numbers of protons and neutrons. Heavier nuclei require more neutrons to offset the increasing conflict from many protons packed into a confined space. Nuclear stability becomes a geometry of internal energy flows. The periodic table becomes a map of stable cycle configurations. Lead, for example, contains 82 protons but requires 126 neutrons to remain stable. This is also why instability leads to beta decay. Too many neutrons, a neutron converts into a proton, beta minus decay. Too many protons, a proton converts into a neutron, beta plus decay. The nucleus adjusts itself to restore cycle compatibility. Nucleosynthesis, where the elements come from. If protons resist being forced together so strongly, how does the universe build the elements? In stars. Their cores reach temperatures and pressures immense enough to overcome the repulsive core and the cycle clash. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, neon, magnesium, silicon, and eventually iron. Iron marks a turning point. Its nucleus is so stable that fusing it absorbs energy instead of releasing it. Beyond iron, only the extreme environments of supernovae or neutron star collisions can force nucleons into heavier elements. The gold in jewelry, the iodine in the thyroid, the uranium in the Earth's crust were all formed in these cataclysmic events. Nuclear structure determines cosmic chemistry. In the nucleus, mass is internal energy held in a stable form.